Alright, welcome everyone to today's class. So, let us finish our discussion of quantum fully homomorphic encryption today, and let's try to recollect what we were doing. So, one of the things we saw yesterday was just how to use a quantum one time pad and a classical PKE to get a quantum PKE that can encrypt quantum states. And then we wanted to think about homomorphism, right. So, we want to have the quantum equivalent of a homomorphic scheme, where when we have some encrypted state, we should be able to apply unitary transformations to that state while it is still encrypted. So, we saw a little bit of a warm up towards this in last class. So, in particular we saw that for Clifford gates, the Clifford group, we saw that there is a nice property, right, this one over here at the bottom. So, we saw that there is this nice property that if you apply a Clifford gate to an OTP of a state, a quantum OTP of a state, then for every sort of secret key x comma z, every OTP secret key x comma z, there is some x prime z prime which allows you to shift this Clifford operator inside. You see this, right? So, we talked about this yesterday. Is this clear to everybody? So, when you do this, then it becomes easy, because what you can do is you can just apply C to the Q OTP, and we have by this property that the C will shift inside, right, and C of psi is what you want to encode. And then the homomorphic encryption of x comma z can be updated to the homomorphic encryption of x prime z prime. So, here we are we did not really spend time on how to compute this x prime z prime. In particular, note that it cannot depend on x z, because x and z are sitting inside an encryption, right. So, we will not be able to open it up and compute x prime z prime according to that. So, we are just taking this on faith for the moment, that you could figure out how to transform x z to x prime z prime without knowing the underlying values. So, this is what we have with Clifford gates, okay. And now the next thing that we need to support are Toffoli gates, and if we can support Toffoli gates, then we will be done. Does everyone agree? Because Clifford and Toffoli gates together form a universal gate set, right. So, we already saw how to handle Clifford. So, now if we can also do Toffoli, then we will be good. And also note here that when we say that we are handling these gates, what we are really doing is we are finding a way to kind of maintain an invariant. The invariant is the structure of the ciphertext, right, which is the QOTP, which has a certain structure, right, and the classical encryption of the QOTP keys, right. So, it is good to remember that. So, that is why I mean handling one Toffoli gate, or one handling each of the set of universal gates is enough, because you having used one gate, you get something which looks like what you started with, right, and you can keep going. So, you can then apply the next gate and so on. So, these are things that maybe we are not making completely explicit, but I hope that this is clear to everybody. Alright, great. So, today's class we will talk about how to handle Toffoli gates, and there is some really interesting theory that that is built in order to do this. And in particular, the paper that we are talking about is by Mahadev, Urmila Mahadev from 2020. It is about quantum fully homomorphic encryption. You can find the reference on the course web page. So, I will not have time to describe the entire construction and entire proof in all detail, but I will highlight the main ideas that make it possible. Okay. So, before we look at the computation, we need to define this new cryptographic primitive, okay, of trapdoor claw free function pairs, and this is something we just did last time. So, just to jog our memory, a TCF function pair is a pair of functions f0 f1 both are injective and have the same image. The main thing that we will use is that it is hard to find a sort of a what is called a claw. So, a kind of a colliding pair. So, you know an x 0 x 1 such that f 0 of x 0 is equal to f 1 of x 1. Okay. But there exists a trapdoor using which you can find it. Okay. So, this is the main idea that the main primitive that we will use. And you know, since we are in the quantum setting, we can actually do quantum stuff, right. So, one of the key ideas that this paper introduces is the idea of having a superposition over a claw. So, let me tell you how to do that. It is a very simple natural idea of how to construct this superposition. You will see that it comes very handy later. Okay. So, let me just tell you how to obtain a superposition over a claw. So, what do you think first of all is the goal here, like when we say superposition over a claw. So, essentially I am given f 0 and f 1, okay, and I want to compute, just as the name suggests, right, a superposition. So, there is some normalization factor of a claw. So, x 0 and x 1 is a claw. So, that means that f of x 0 is equal to f of x 1. Okay. So, this is something that I want to do. The goal is clear, okay, and I mean we have done this dozens of times by now, right. So, in fact, I am pretty sure that all of you can guess how we will do this as well, right. So, basically I mean I just define the right kind of function, okay, and then I compute the function as we have done before. Then I do a partial measurement that gets it to collapse to, you know, superposition. We have done this in almost all the algorithms that we have seen. Okay. So, let us not spend a whole lot of time on this, let us just outline the steps. So, how to do it? Okay. So, first So, first you know I prepare a uniform superposition. So, what is that? Well, okay. So, I prepare this uniform superposition. Okay. What is it? So, it is summation over, you know, all bits b and all strings x of lambda bits b x 0, all right. So, step 1 is to prepare this uniform superposition. Okay. Now, step 2 is very natural, it is what you would expect. So, now I define a suitable function, right. Can anyone think I have f 0 and f 1, how should I define my function so that I get a superposition of the clause? So, my input is, you know, some b x and here it is 0, but let me just call it y. What should my function transform this b x y to? Yes? Very good, exactly. I mean, so to be a little more precise, so b x f b of x XOR y, right. So, for us y is 0, so XOR y will just it will just be 0. So, this is exactly right. So, basically I want to get a superposition over the clause. So, I want to use my bit to select the function and I apply this function. Okay. So, we get sort of summation over b comma x, b x and fb of x. Okay, so great. So now what should I do? So this is stuff that everyone's an expert in by now. So now what should I do? If I want a superposition over the clause, so one of those keywords was indeed correct. So you know, measure the last register. So if I measure the last register, what is going to happen? So you know, fb of x will collapse to some y, right? And then I'll get a summation on x0 and x1 such that f0 of x0 is equal to f1 of x1. Okay, so I will get summation of x such that fb of x is equal to y b xb, okay, and of course y. So there's some y. So this is just to say that we can do it. Okay, so I'm going to, as usual, discard this. So essentially what I got is 0 x0, right, plus 1 x1, where f0 of x0 is equal to f1 of x1. This is what I wanted. Okay. Now you may be wondering, what does this have to do with Toffoli gates? We will get to that. So this is just a little bit of machinery that we have set up. Okay. Good. So are there any questions? Shall we go on? So let's go back to the frame of our story, which is of course QFHE, right. So this what we just did was something that we need to use along the way, but of course what we are trying to build is QFHE, right. And once again, so we said we want to support Clifford and Toffoli, okay, and this we already know how to do. Okay, so we want to do this now, and also it is not a bad idea to sort of recollect what is this Toffoli gate. So it is a 3 input gate, right, A, B, C. So A goes to A, B goes to B, okay, and C goes to C XOR A, B. So it is a controlled C naught gate, right. Yeah. So if C is 1, then it control, then I mean this is C is the control bit here. So if C is 1, then the C naught gate gets computed. Okay. So so now we want to support this gate, and we are starting with some state, right. So we are starting with some QOTP state, which looks like x to the x, z to the z psi. Okay, and what do we want to do? So remember that our hope was to sort of put a t inside here, right. We do not mind changing the x prime x z to some x prime z prime, but we want to insert one t over there. And what happens if I simply do the obvious thing? So what is the most obvious thing I can try? Apply t to psi prime, which I have, right. So let me try that, right. So if I do t of psi prime, what do I get? So I get t x to the x, z to the z, and because I want t over here, let me just do t dagger t, right. So that is identity. So I can always write that. Now if I could have expressed this as some x to the x prime, z to the z prime, then I claim I would be done, right. This is what we did with the Clifford gates. So if it were possible for me to club these terms together to get like a a well formed OTP like structure, then I would be in good shape, and I could just apply T and try to update the classical homomorphic encryption, and I could proceed. The problem is, of course, that we cannot do this. So, in Clifford gates there is a particular structure that lets us do it, but in Toffoli gates there is not. Okay. So, we do not know how to do this. So, what we will do is we will actually do some elaborate thing to convert this this to the form that we want. So, it does not work automatically, we will have to do a bunch of things to make it work. Okay. So, we need to convert it to this form. Okay. So, it does not just work. Okay. So, now how do we want to do it? So, one more thing that it does not hurt to recall is that our QPKE, what does it look like? It is a QOTP, right, and a CPKE. So, here C stands for classical and Q stands for quantum. Okay. So, this is what it looks like. So, and what I want to play with is this thing here, right. So, I want this T x to the x, z to the z, T dagger. This is what I want to somehow massage, right. I want it to look like some x to the x prime, z to the z prime. That is my goal over here, right. So, okay, what to do? So, now one fact that we will use is the following. So, it turns out that if I open out this expression in terms of C naught gates and poly gates, then this looks like the following. Okay. So, first of all, observe that x to the x and z to the small z. So, this small x and small z are how many bits? 3 bits in fact, right, because we have 3 bits that are input to our gate. Good. So, I can write this as in longhand, I can write this like this. T dagger. I mean, this is just rewriting it in terms of individual bits, and it turns out that you can open this up to get the following. So, C naught of x 2 1 3. This notation here means that this whatever is in the superscript. So, x 2 over here, this is the control bit for this C naught gate, for this gate. Okay. So, C naught x 2 1 3, okay, then C naught x 1 2 3, then z hat 3 1 2, okay, then x to the x 1 z to the z 1 plus x 2 z 3 tensor x to the x 2 z to the z 2 x 1 z 3, okay, tensor x to the x 1 x 2 plus x 3, z to the z 3, okay, where z hat is I tensor Hadamard of C naught z 3 1 2 I tensor Hadamard. Okay, great. So, for the sake of completeness, I have written out this big expression. I did not derive it, this is just a fact. okay, you could verify that this is correct. So, also let me just write that here C naught I j y means that C naught I j is performed if y is 1. Okay. So, we have this long complicated expression. What can we get out of it? Any thoughts? I mean, it may be a bit hard to guess, but does anyone notice? So, let me try to sort of direct us a little bit here. So, let us try to think in terms of gates, right. Like we know how to handle Clifford gates, right. We know how to handle in particular Pauli matrices or Hadamard gates and so on. So, I want to say that this thing inside the parentheses, okay. So, this stuff here. I want to point out that this is just Pauli matrices, right, Pauli operators. Similarly, this H is just a Hadamard, so it is a Clifford gate. And where I am going with this is that basically the gates that we do not quite know how to do are these, right. These are the gates that we do not quite know how to do, and the crucial observation that was made by the author is that the control bits of these gates are actually all classically encrypted. Okay. Okay, so let us write this down. Okay, so the observation is that the control bits are classically encrypted. Okay. So, it turns out because of this that in order to support encrypted Toffoli computation, it actually suffices to support encrypted C naught computation. Okay. So, basically if I could do the following, right, that I have enc of S, right, A, B, and I get here enc of S, okay, A, B, XOR A S. Okay, so it suffices to support, well, I should not just say suffices to support encrypted C naught. What I mean to be a little more careful is that it suffices to support this circuit that I have here. So, where the control bit is classically encrypted, okay, I have some inputs A and B, right, and I want to end up with B XOR AS, and moreover I want this B XOR AS to actually be encrypted. So, I want this encryption to actually be a classical FHE, okay, and I want this encryption to be quantum. Now, first of all, observe that it is crucial that this B XOR AS be encrypted. Why is that? Because I want S, I mean my S here is encrypted, right. So, presumably I want to hide S. If I do not encrypt the output B XOR AS, right, then I could set A equal to 1 and B equal to 0, and this would give me S, is not it, right. So, I want to get the output state also to be encrypted. So, let us just take a step back. I hope that things were clear. I mean we stared at this big expression and observed that the control bits of these gates are all classically encrypted. So, without doing a very careful proof, we at least intuitively concluded that it suffices to compute this particular gate, where I have the control bits as encrypted, right, and I compute this C naught over here. The output should also be encrypted, but the output should be encrypted quantumly. Okay, so is it clear? I think it is really sort of cool, right. So, I mean really staring at the structure of the problem and figuring out that you know here is what would suffice. Now, note that actually at this moment it is not clear at all how you might support something like this, right. So, it is not clear at all how we would support something like this, but you know let us keep going and well, she does it, right. So, we are not presenting this if she had not succeeded. So, there is a very clever way in which this problem can be solved. So, good. So, this is what we want to do. Okay. So, now let us focus all our attention on this. Okay. So, let us focus our attention on this encrypted C naught gate. Okay, so what do I want? So, formally given a quantum state, so we are given this this state, okay, and let us denote C naught S psi as this, okay, and what we want is that, well, I want to be able to put this in a box, right. So, I want to have C naught enc of S, okay, this is FHE enc of S psi, okay, going to quantum enc of the above state. Okay, great. So, presumably we made some progress. I mean at least we have reduced our problem down to something simpler, at least that we have done, but it is still not clear at all how to do this, right. So, we want, so yes, we want this, indeed we want this. How do I do it?